Okay, maybe we should start and people will join us as we speak. So this is the last BHI colloquium of the academic year, and it has been an unusual and difficult year. And we hope Harvard made a statement that on August 2nd, everyone will be back to campus. So we hope to open up the BHI corridor at that point. If you have any questions about the administrative details, please contact Nicole. At that time, we're allowed to be back to the building. So August in about a couple of months from now. And I hope everyone had the opportunity to get vaccinated, because at least for the students, it's a precondition for coming back to campus. But overall, it looks like the situation is very promising. Also, I wanted to mention that next academic year, I will be taking a sabbatical, so I won't be around as much as I used to. But Peter Gallison is taking over. He will replace me as the BHI director. And Peter, are you there?
Yes, I'm here. And
so if anyone has issues with respect to the next academic year, please approach Peter. As I mentioned, I will be away on sabbatical. And the other thing I wanted to mention is we will be adding two senior members, PI, principal investigators, to the BHI. There will be Priya Natarayan and also from MIT,
Netta Engelhardt.
Netta Engelhardt, yes. So these are two additional senior members, and they will start in the coming academic year. Will be joining us. Priya spends time in Cambridge, so she will join for the colloquium, and Netta, obviously from MIT, can join us quite easily. Peter, did you want to add any additional?
No, the only other thing is I've been in discussion with Chris Stubbs, the Dean of Sciences, and it may be that all the sciences will open up even sooner than August 2nd. I will keep everybody posted.
Okay. Sounds good. And without further ado, we should let Fabio introduce Giacomo, who happens to be my close collaborator. So I'm very glad to see him in our last BHI colloquium for this year.
Yes, so today, for the last BHI colloquium of the academic year, it is my particular privilege to introduce Giacomo Fragione. Giacomo is currently a CIERA fellow and a research assistant professor at Northwestern University since 2019. And from 2016 to 2019, he was a fellow of the Israel Academy of Sciences and Humanities, the Arskin Fellow, at the Hebrew University of Jerusalem. He obtained his PhD at the Sapienza, University of Rome, and University of Tor Vergata in 2016. And today, the intriguing title of his talk is Intermediate Mass Black Holes, Love It or List It. So please, Giacomo, take it away.
Thank you, Fabio, for the introduction. And thanks for organizing the talk. So yeah, so it's my great pleasure to be giving this talk today. And unfortunately, it's like I have been visiting Avi regularly every year almost since 2016. So at least, this year I can give this remote talk, and I hope that I will be able to visit Cambridge soon when everything will be back to sort of normal. Okay, so yes, so I will go and talk about intermediate mass black holes, love it or list it, and I immediately tell you the reason why of this title. Maybe some of you are familiar with this TV show. So this TV show is actually called Love It or List It, and it's basically these two people that were essentially a couple, and they have a house, And so one of the guys wants to keep the house, refurnish it, and the other one instead wants to sell the house, list it, and buy and go to a new house. Okay, and so basically the theme of the talk will be essentially that during the talk I will be listing several motivations for which we have to either love intermediate mass black holes or list intermediate mass black holes and maybe move to some other research field. Okay, so let me start with what I call intermediate mass black hole existentialism. Okay, the reason for that is that so first of all, we know that there is the spectrum of compact remnants from star revolutions. Okay, so we know that the low mass stars will give us eventually white dwarf and neutron stars, while the more massive stars will eventually collapse and form stellar mass black holes. Okay, so these black holes have masses, say, more than 5-10 solar masses up to 100 solar masses. Okay, on the other hand, we know that the center of galaxies host supermassive black holes, so black holes that have a mass more than 10 to the 5, 10 to the 6 solar masses. Okay, what is in between is what we call intermediate mass black holes. Okay, so actually intermediate mass black holes are usually defined for not what they are, but for what they are not. So essentially, it's everything that is not either a stellar black hole or a supermassive black hole. And essentially, the questions we have for intermediate mass black holes are the same questions that humans have had since the beginning, right? So what are intermediate mass black holes? Where are intermediate mass black holes, and how intermediate mass black holes were formed? Okay, so now the question is, among these three questions, I think that the most important one is this one: where are intermediate mass black holes? And the reason is that if we observe supermassive black holes, it's clear that at some point in time we should have had intermediate mass black holes that then accreted mass or grew in mass and gave us supermassive black holes. And based on that, based on our ability of finding where intermediate mass black hole are, we can then answer the other questions: what are intermediate mass black holes and how they were formed? Okay, so why are intermediate mass black holes interesting? Okay, so because intermediate mass black holes have a lot of potential, not only gravitational potential, but also potential in terms of understanding a few important questions. So for example, one of them is first, if we can extend the scaling relations we know exist for supermassive black holes and galaxies that host these supermassive black holes. Okay, an example of that you can find in this plot. This plot is the very well-known M sigma relation that connects basically the mass of the supermassive black hole at the center of the galaxy and the velocity dispersions of the stars around it. As you can see, we have here data points till like 1 million solar masses for the supermassive black hole. So if intermediate mass black hole exists and we find them, we can try to extrapolate and understand how this relation goes down, to a few orders of magnitude, like to 10 to the 3, 10 to the 4 solar masses. The second thing is that intermediate mass black hole will allow us to understand better the accretion mechanism, okay? Because we know how stellar mass black holes, for example, accrete from companions like in the form of X-ray binaries, and we know also how supermassive black hole accrete and behave in the center of the galaxies in terms of accretion. So the question is, at which mass do we have the transition between something that looks like an X-ray binary and something that looks like an accreting supermassive black hole or an AGN or something like that? Okay, so, and this obviously happens to be in the regime of the intermediate mass black holes. Then third is evolution of dense star clusters, because again, as the supermassive black hole influence the evolution of the galaxies that host them, also intermediate mass black holes that are hosted very likely by some dense stellar environments, as I will show you in the next slides, will affect the evolution of the host star clusters. And then obviously people have been looking at intermediate mass black holes, both in terms of electromagnetic counterparts like tidal disruption events and the gravitational wave sources, since they are one of the main sources for next generation instruments like LISA. So let me then list, these very broad implications under the calm law of it. Okay, so this is like something very important. We have many implications for intermediate mass black holes, and something that we want to pursue our research on intermediate mass black holes. So how do intermediate mass black holes form? So already Rees back to 1978 had sketched, what is like more or less what we still think today is the way that we form intermediate mass black holes. Okay, so there are a few mechanisms. So we have essentially 4 main mechanisms. The first one is essentially that we have a gas cloud of pristine composition, so with low metals. So this gas cloud can directly collapse and form something that is of the order of 10 to the 4, 10 to the 5 solar masses. Okay, the second channel is so without passing essentially through all the phases of stellar evolution. The second channel is that instead, if this gas cloud collapses to form first a very massive star, and then this star will evolve and eventually collapse to an intermediate mass black hole. So in this case, models predict that the mass of these objects is typically of the order of 100 solar masses. Again, these two mechanisms obviously can only take place at very high redshift because we need a pristine composition, so with low metals, okay? So the other two mechanisms involve dense star clusters, okay? So because what can happen? So in dense star clusters, what can happen is that, so first of all, if the cluster is massive and dense enough, so stars can accumulate via dynamical friction, so they will sink to the center of the cluster and will start interacting among themselves. And since if the cluster is very dense, the stars will merge with each other and form a very massive star that eventually will collapse to an intermediate mass black hole. Okay, so models in this case predict that this process, it is called runaway growth, produces intermediate mass black holes in the range between 100 and 10,000 solar masses. The second case is in which instead we do not have the merger of many stars, but first these stars collapse and form neutron stars and stellar black holes, which then will themselves be in the center of the dense cluster, and then at that point they will start interacting and merge with each other. Okay, so in this case, again, an intermediate mass black hole can be formed through repeated mergers of stellar mass black holes, essentially, and models predict that the typical mass is of the order of 10 to essentially 100 and 10 to the 10,000 solar masses again. So let me unfortunately list this, under the column list, okay? Because essentially this is very challenging, okay? This is one of the motivations why we might have some difficulties in observing, and understanding what are the targets of our observation, because it's like very challenging under the theoretical point of view to understand how we form intermediate mass black holes. But nevertheless, let me just give you a few points about how we form intermediate mass black holes through runaway growth and repeated black hole mergers in a dense star cluster. So in this plot, you can see what we got in a paper last year. Okay, so in this paper, basically we showed how we can form intermediate mass black holes in a dense star cluster that starts with some, quite dense. So what happens, as I said, as you can see, this is like a merger tree. And so stars start merging with each other, till the point they will grow in mass and eventually collapse, forming some stellar mass black hole. Okay, so now why this mechanism is interesting? So it's interesting essentially because we know from stellar evolutionary models that we have a process called peri-instability supernova that either completely disrupts black holes. Okay, so in this case we have a peri-instability supernova that essentially where essentially there are no black holes, predicted black holes to exist between like 40, 50 solar mass and 120 solar masses, and we have the so-called peri-pulsation instability supernova, where instead in this case stellar black holes, so the progenitors of stellar black holes will be pulsating and ejecting some mass till the point they will collapse to a black hole whose mass is of the order of 40 solar masses. Okay, so and for any reasonable initial mass for stars, okay, so if we trust what we know about the initial stellar mass function, okay, so the maximum mass for stellar black holes that we can create is of the order of 40, 50 solar masses. Okay, this limit depends a bit on the metallicity. Okay, so and essentially there is no way to form, starting from the initial mass function, to form black holes that are more massive than 120 solar masses. Okay, but this can happen only if we start merging stars together. And we showed in 2 other papers this year that actually all this process, all this business depends apart from the initial density of the cluster. So that has to be like high enough to have stars merging together in, as you can see here, the time scales is just, a few mega years, okay? Before essentially the stars start exploding as supernovae. So all this business depends a lot on the density of the cluster, but also on the primordial binary fraction, so essentially how many massive stars are in a binary to start with, and also on the slope of the initial mass function itself, on which we have some uncertainty. Okay, so this process is called like runaway growth, is the fast way to produce intermediate mass black holes in a dense environment through repeated mergers of stars. So the other process is when we repeatedly instead merge, instead of stars, when we merge stellar mass black holes. Okay, so first stars collapse to stellar black holes and stellar black holes will merge with each other. So now there have been a few papers in literature now looking at this, okay? The main problem in this case is that whenever you merge two compact objects, if the compact objects are not symmetric, so you have an asymmetry in terms like of mass, for example, they will get a recoil kick because of the asymmetric emission of gravitational waves. Okay, and this recoil kick, moreover, is larger for larger intrinsic spins of the black holes. Okay, and so the point is that whenever you merge two black holes, you can get recoil kicks that are as large as a few hundreds up to a few thousands kilometers per second. Okay, so this means that the only places where you can get these repeated mergers are places that are dense enough, that have escape speeds that are on the order of a few hundreds kilometers per second. And so this typically is just, the very, very massive star clusters we observe, like, for example, nuclear star clusters or super star clusters. And again, all this business, so we have a paper in preparation on this, so that hopefully will be out soon, and all this business, again, depends on the details of the dense star cluster. So apart from its initial density, it depends also on the primordial binary fraction and also on the slope of the initial mass function itself. And this process, as you can see, I called it slow because, as you can see on the x-axis here, it takes like up to a few gigayears to get something in the range of the intermediate mass black hole. So now just let me say how we look for intermediate mass black holes under the observational point of view. So essentially, there are 4 main ways to look for intermediate mass black holes observationally. So the first one is to look for stellar and gas dynamics. Okay, so model stellar and gas dynamics in an environment where we think there might be an MBH. So the second thing is like modeling the accretion. Okay, so in some place where we see like some accretion signatures, we can try to understand if this accretion is due to some intermediate mass black hole. And then the other 2 ways are, total disruption events. So essentially, if a star or a white dwarf passes too close to a massive black hole, it gets swallowed and it gets accreted part of the material. And so this can give us some electromagnetic signal, and we can observe that and try to infer the mass of the black hole that swallowed the star or the white dwarf. And finally, gravitational waves, obviously, through LIGO, LISA, and all the upcoming instruments. So I will go through all of them. So first of all, if we look at dynamical signatures, the way we do this, the way people that do observations do this is essentially they look at something like this. Okay, so here you have like the velocity dispersion you observe as a function of the distance from the center of the environment you're looking at. Okay, so in this case, we have this galactic globular cluster, omega sen. And so this is the velocity dispersion. And so you expect that this should be like sort of flattish here. So if you see like some data points that, are start increasing, this might be the signal that there is an intermediate mass black hole. And the reason for that goes back to the pioneering work by Bacall and Wolf in the 70s, where they showed that within the sphere of influence of a black hole, that is defined essentially with the sphere within which the dynamics at the lowest order is dominated by the black hole. So within the sphere of influence, stars and compact objects follow a Caspi distribution. Okay, so and essentially, the closer to the center, the denser the objects are. Okay, so now, first of all, we have a problem, because if we take the most massive intermediate massive black hole we can think of the order of 10 to the 5 solar masses, because otherwise then we go to the regime of supermassive black holes. And we put this at 10 megaparsecs, so in the very local universe, you can see that the sphere of influence it's just 0.01 arc seconds. Okay, so this is very resolvable with present and future instruments already. And moreover, so this causes, like large error bars, in your measurements, and also misleading conclusions. And moreover, on top of that, you have to add that you have to have an body model, like a theoretical model of the cluster that you have to use to fit the data you observe. And doing this is not easy with any code that there is on the market, because anytime you have an embodied model and you put at the center a very massive black hole, you have to make a lot of approximation, okay? And this led, for example, for the same cluster here, Omega Sen, NGC 5139, to be claimed, in, oh, sorry. Can you see my screen?
No, it's white.
Oh, I don't know what happened. Sorry about that. Something happened.
We see your desktop now.
Oh, okay. Sorry about that.
Yeah, no problem. Yes.
Okay, you can see now. Okay,
yes, we see
cool. So as you can see, so what I was saying is that, essentially for the same cluster, people claimed, both that there is an intermediate massive black hole of 40,000 solar masses, and a few years later that there is not. Okay, so this is just to say that this is very difficult modeling. Okay, and moreover, all of this, this signature is also degenerate with a possible anisotropy in the velocity tensor of the cluster itself. So essentially, if you have an anisotropy in the velocity distribution, this can mimic the presence of an MPH. And moreover, if you go, instead of globular clusters, if you go like towards like galactic centers, where you can have like IMBHs of 10 to the 4, 10 to the 5 solar masses, everything is even more complicated because of ongoing star formation, dust, massive stars that make everything much more complicated. Okay, and so just to mention that for our galactic center, people have done some dynamical studies and they've eliminated part of the parameter space that you can see here. So this is essentially the possible same major axis of the companion to Sagittarius A star as a function of its mass. And so as you can see, so all these things have been eliminated, have been constrained based on dynamics or the evolution of the radio source that we observe in the galactic center. And so there is still a tiny part of this parameter space where a companion might exist. Okay. So unfortunately, I have to list dynamical measurements because, as I showed you, they are very complicated, and it really depends on the accuracy of the models and of the observations, but it's not easy at all. So now let's go to the accretion signatures. Okay, so accretion signatures is essentially, okay, so people are looking at observations and they see something that is accreting. Okay, so they want to model the black hole that is giving this accretion. Okay. And so this typically is done for like intermediate massive black holes that are quite very massive, of the order of 10 to the 4, 10 to the 5 solar masses. And so this is usually done in the context of galactic nuclei. Okay, so what people do is they use these kinds of plot where essentially according to what they measure in terms of the emission lines, they can understand if it's like a real emission, like a Seyfert galaxy, so an emitting black hole, or it's just star formation. Okay, so and in this case, in this paper back to 2015, in this particular galaxy LGG 118, you can see that. So using this method, people have claimed the presence of a black hole of 50,000 solar masses. And so essentially the practical way to do this is to look and model the emission lines, then use a sort of virial equation. And through this virial equation based on the sides of the lines, on the width of the lines, you can infer, given a modulo like some constant, you can infer roughly the mass of the black hole. Okay, and you can see that typically this can be done reasonably well for intermediate mass black holes that are 10 to the 4, 10 to the 5 solar masses, even though sometimes there is confusion because of star formation or supernova remnants, or whenever you observe a gas, the gas might not follow virial trajectories, but might follow hydro trajectories or non-virial trajectories. Okay, and something similar, some X-ray emission modeling has been done also for the so-called ultraluminous X-ray binaries. So essentially X-ray binaries that we observe that are too luminous to be explained with neutron stars or black holes. And so historically, a few of them have been claimed to be caused by intermediate mass black holes. But recent analysis has showed that just one of them, HLX1, is consistent with an IMBH, okay, cannot be explained with either, with no model like for neutron stars or black holes, but this should be given by an intermediate mass black hole of 10 to the 4 solar masses. Okay, so accretion signatures, you know, are somewhat good. You know, we can trust, you know, most of them, in particular for very massive black holes. So let me put them under the love column. So now, what about tidal disruption events? So tidal disruption events, as I told you, is essentially the process during which a star or a white dwarf passes too close to a massive black hole, and the massive black hole, the tidal field of the black hole will overcome the binding energy of the system and essentially will disrupt the star or the white dwarf. So this we expect for intermediate mass black holes to have an overall luminosity of the order of 10 to the 41 ergs per second, and to shine, you know, in X-ray and optical. And what's interesting to this regard is that while stars can be disrupted by both intermediate mass black holes and supermassive black holes, and actually the tidal disruption events that we have observed are all coming from the center of galaxies from supermassive black holes. White dwarf can only be disrupted, and their signal can only be observed if the disrupting massive black hole is in the intermediate mass black hole regime. So essentially less than roughly 10 to the 5 solar masses. And the motivation of that is that for white dwarf, so any black hole more massive than 10 to the 5 would have its Schwarzschild radius larger than the tidal disruption radius of the white dwarf. So essentially we have that we do not have like a tidal disruption, but we have essentially that the white dwarf we directly plunge onto the black hole, and we would see nothing since this will happen within the Schwarzschild radius of the black hole. And so you can see actually that, you know, in these couple of papers here, there have been like a few claims of X-ray white dwarf disruption events candidates. But let me mention in particular this other case, you know, from this galaxy that you can see here. In this case was a star that was tidally disrupted by a black hole. Okay. And so you can see here all the characteristics of the galaxy. So it was like a lenticular galaxy with like 10 to the 11 solar masses roughly in the very local universe. And this TD, very interestingly, happened not in the center of the galaxy where you expect to find a supermassive black hole, but at roughly 12 kiloparsecs from the center. And in this paper in Lin et al. 2018, people estimated the intermediate mass black hole to be of the order of 50,000 up to 10 to the 5 solar masses, and estimated a rate of 10 to essentially 1 in 10 million years per megaparsec cube, so 10 to the minus 8 per megaparsec cube per year. Okay, what's interesting about that, as I said, so first of all, it's not coming from the center of the galaxy where all the tidal disruption events we know of are coming from. So essentially, by massive black hole, it's coming from some cluster that is in the outskirts of the galaxy. So, and it happened that just a few days after this discovery was made public and published, we got this paper, we submitted this paper where essentially we took a model. We developed, you know, for the first time, a self-consistent model of star clusters forming in a galaxy and evolving within the tidal field of the galaxy, and at the same time having the intermediate mass black hole, you know, shredding stars and white dwarfs. And so we came up with rates that were pretty close to what they found in the observational paper. And also you can see here, this is like the typical distance at which we modeled, we found in our models these events happening. That was around 10 kiloparsec in a galaxy that has the same mass of the galaxy, of the observed galaxy. So we had pretty good match. Okay, so it's like, also in this case, we are pretty confident that this is an intermediate mass black hole. And so let me put this under the Leavitt column. Okay, so tidal disruption events are definitely a powerful tool to observe and find intermediate mass black holes. So next on the line, it's gravitational waves. Obviously, let me say, this is probably the most detailed way we can find intermediate mass black holes and black holes in general, because we can essentially model various phases once we will have like space instruments like LISA here, and once we have here, ground-based observatories, we can, model from the in spiral to the merger and the ring down of the systems with, within a few years. So essentially the people working in LISA will be able, to send alerts, to their friends in the LIGO, ET, Einstein telescope, or all the other planned instruments, and saying, okay, look, in a few years, in a few days, you are going to observe, some merger ring down of this event in your frequency band. And so these actually, intermediate mass black holes offer a very powerful way, to observe the same event, in the space observatories and in ground-based observatories, within a few days or a few years. And actually, so far we have that, LIGO, Virgo has estimated, upper limits for these events, for the black holes that are a few hundred solar masses merging with stellar mass black holes. And they found that this limit, the rates are between 0.1 and, a few tenths of gigaparsec cube per year. And indeed, LIGO was able last year to find the first confirmed intermediate mass black hole coming from the merger of two stellar black holes of roughly 90 and 60 solar masses, producing an intermediate mass black hole of 150 solar masses. So the very well known GW 190521. Okay, and so this just to show that gravitational waves are very well suited to do this job. And to this regard, I just a few days ago, my proposal to LISA to model, and give models for to LISA NASA to model, intermediate mass black hole formation and mergers has been accepted and founded. So I have a lot of interest in this, and and if people are interested, in collaborating, on finding, modeling intermediate mass black hole mergers in LISA band, just send me an email, and we will be very happy to discuss this. We have a very nice collaboration between Northwestern University of Florida and Johns Hopkins. So yeah, so in terms of models, so far there have been we have developed a few models that have some obviously some limitations that we hope to lift in our upcoming studies. But as you can see here in these models, you can see that the rates that we are predicting with our models so far are roughly consistent with what LIGO is predicting, so the order of a fraction of gigaparsec cube per year. And also that so if we look here at how many mergers we should find using LIGO, Einstein telescope, and LISA, you can see that we expect during the LISA lifetime, so of roughly 4 or 5 years, we expect to find hundreds of these mergers at least. But at the same time, intermediate mass black holes need an improvement, apart from models, also from modeling the waveforms, okay? Because intermediate mass black holes lie, in this gray area between the stellar mass black holes, where we know very well, from the LIGO experience, like people know very well how to model the waveform of these objects, and the extreme acceleration spirals. Essentially, when you have a stellar black hole merging with a supermassive black hole, and giving you what people call extreme acceleration spiral. Okay, so in that case, there are other kinds of approximations and perturbation theories that you can use to model the waveforms. But intermediate mass black holes are, in the gray area, so probably, we need to also have improved improved waveforms. And obviously, and so these are what people usually refer to as intermediate mass separation spirals. Okay, so basically intermediate mass black hole, stellar mass black hole mergers. And let me mention that also, we obviously, other kinds of mergers involving intermediate mass black holes are when intermediate mass black holes merge in galactic nuclei with supermassive black holes. So with that said, just let me put also gravitational waves under the love column. Okay, so gravitational waves are a very powerful tool, and like in the next decade or so, we will definitely be able to find many intermediate mass black holes this way. So just let me recap a bit, the mass spectrum. So as I showed you, intermediate mass black holes in galactic nuclei extend, up to 10 to the 5 solar masses, and these have been observed, quite, in a few galaxies now through accretion signatures, in particular, and also modeling of ultraluminous X-ray binaries and tidal disruption events. We find, some good evidence for intermediate mass black holes of 10,000 solar masses to exist. And like LIGO Virgo through GW 521 showed that intermediate mass black holes of 100 solar masses or so exist. So the question that we are left with is like, where are the intermediate mass black holes with 1,000 solar masses? So just let me wrap up with here in a couple of slides. So first showing that what is the future. Okay, so you can see here like the number of expected detections per year as a function of the distance and then of the redshift. So here essentially in the local universe, and here in the far universe, in the distant universe. So in color code you find the mass of the intermediate mass black hole that we think we could find. Okay, so you can see here that using, so fundamental plane essentially refers to X-ray and radio emission. Using dynamics and probable motions, we will be able to probe just the local universe, okay, with upcoming instruments. But like using other kinds of signals like AGNs, tidal disruption events, intermediate mass black hole, stellar mass black hole mergers, or gravitational waves, we will be able to probe intermediate mass black hole demographics up to the distant universe, up to a redshift of a few. Okay, and so let me list this, under the, obviously the bright future for intermediate mass black hole under the love column. Okay, and so as just to wrap up, as they usually do in the TV show that I showed you in the beginning, love it or list it. At the end of the day, the couple we decide either to stay in the house or to move to a new apartment. And so you saw this coming. What are we going to do with intermediate mass black holes? We are going to love it. Okay, so we have many reasons, to investigate intermediate mass black holes. They are very rich, in observations, and in the future, many of them will be definitely found through different observational methods. So yeah, so I will conclude with this sketch of GW 521, and I will be happy to take any questions. Thank you.
All right, Giacomo, that was a really interesting talk. Thank you very much. I just wanted to comment that it's better that we love them, because it would be a little bit hard to sell them. I don't know if there is exactly a market for intermediate mass black holes. But yeah, there's one comment and one question already. So I just wanted to read Martin Elvis' comment that said that broad emission line characteristic of AGNs with mass of about 10 to the 6 solar masses become much weaker below 10 to the 5 solar masses, because the disk continuum becomes too hard and over ionizes gas within a Keplerian velocity above 1000 kilometers per second. So this leads to a selection effect against finding intermediate mass black holes in galactic center.
Yeah.
And then there was a question from Aditya Tamar. Sorry if I don't pronounce this correctly. Thank you for the informative talk. Do we have a grasp over the range of spin of these intermediate mass black holes through either accretion signatures or LISA models?
Yeah, so definitely, so definitely spins, so it depends obviously, like how you form these intermediate mass black holes, right? So for example, just if you go to the case where where you form them in star clusters, through either mergers of stars or mergers of black holes, for example, if you have like mergers of stars, uh, like you might have, like a spectrum, of spins, maybe the star that, will collapse and form an MBH, maybe will spinning or not. But, if we think that, oh, sorry about that. So if we think that, so there is, so if we trust, current evolutionary models where like massive stars will collapse to black holes with almost no spin, probably black holes coming from this model will have no spin. Okay, while in the case you come from you come from repeated black hole mergers, we know very well from numerical relativity that the black holes as they merge will start increasing the spin, going towards the region of 0.7 in intrinsic spin. This will eventually become smaller. Okay, so and also for AGNs, it will depend essentially on the rate of accretion and so on. But definitely, these things, I think, so they can definitely be understood. For example, for gravitational waves, the waveforms and models will definitely depend on the spin and the eventual precession given by the spin. And exactly as when LIGO Virgo model their stellar black hole mergers, the waveform will depend on the spin. It will inform about the spin eventually of the black holes.
All right, so we have a question from Avi.
Yeah, so Giacomo, that was very nice. One question about the abundance that you estimate. Is there a break? I mean, do you have an estimate for the abundance? Is there a break relative to the more massive black holes, supermassive black holes, in the sense of those intermediate mass black holes being much less abundant or much more abundant? Or do you know if there is a break relative to stellar mass black holes? Because, if we see a continuation from either end, either the low mass end or the high mass end, that could say something about how they form, whether they form by gas accretion or mergers in star clusters and so forth.
Yeah, I mean, there is, I think that, like, these, the exact, boundaries here, are pretty unknown. It's not exactly clear, and also, so I mean, and essentially I agree with you that this would be like something very good, to have, and because, eventually we expect, there is no reason to think that there is like a break here, in the black hole mass function, but there should be like some continuum, like some continuity here. So, and maybe the break is somewhere here, we don't know, but I think that as we have like more statistics either coming from gravitational waves or accretion, whatever, we will be able to explore this. And in terms like of the occupation fraction, like also this, it's like it's like very difficult to grasp. It's like so in a given galaxy you can have multiple intermediate mass black holes, because either you form them in star clusters, or maybe you form them around AGNs, because if the AGNs have disks, you might form an intermediate mass black holes, or maybe either you form them like from on a bigger scales, like coming from more from bigger cosmological pictures, so definitely you can have occupation fractions that are more than one, unlike the supermassive black hole case. But if it's like one more than one, less than one, in my opinion, it's still very, very.
Yeah, I mean, especially if they form in the course of dwarf galaxies, they can be easily kicked out by recoil if there are mergers, and and so you could have many intermediate mass black holes forming per galaxy based on the merger tree. And you're right.
We have like so one of our students here, she's so a couple of our students, they are essentially, we had these two papers. They are continuing, investigating this, and so some preliminary results show that essentially, so if massive stars were born with 100% of binary fractions, so essentially all of them were in binaries primordially. Okay, as we observe, in the field. So in the field, we observe that all the massive stars are in binaries. Okay, so if this happens also in primordial clusters, okay, so it turns out that most of the clusters will produce something that is on the order of a few hundred solar masses. But as you said, this guy will immediately be ejected as it meets and merges with the first black hole. And so this means that, like maybe, in the globular clusters we observe, we might not have any more intermediate mass black holes, but maybe the galaxy has hundreds, thousands of them just because of this process. But the way to find them like here in the dark, because they might not have any other companions, it's not easy. You should be like maybe lucky to observe them through lensing, or I don't know, or something like this. It's quite tricky there.
Thank you.
Angelo.
Giacomo, thanks for a great talk. I was intrigued about your predictions of TDE rates for intermediate mass black holes and clusters. And I was wondering, this probably is sensitive to the occupation fraction of black holes that you must assume in these globular clusters. So what are your priors on that? Do you think it's plausible that all of them might host a black hole? And then second, is this sensitive to the structure of the cluster itself?
Yeah, very great question. So you can see here, so in this paper, you can see plots like this, where essentially, so these plots are, integrated over all the clusters in the galaxy, and assuming that every cluster was born with an MBH that was like 1% of its initial mass. Okay, so now this is like the most optimistic case, but if you scale this, by saying, okay, like some simulations tell us that like probably 10-20% maximum clusters might have an intermediate mass black hole in the beginning, and this might be retained. And if you scale this by the number of clusters you have in a given galaxy, you end up with rates that are of this order of magnitude, like instead of say -2, -4, like down to -7, -8. But definitely, these are based, since. So these models, are quite complicated if you were to do this, realistically, with an embodied code. We just we applied, several approximations. Like we use like several semi-analytical equations. Some effective, loss cone theory and so on. We came up with these rates that seem reasonable, but definitely there is, a lot to improve upon this, and obviously, also we adopted, some fitting formula, for example, in this case for the cluster and galaxy structure. We didn't model, obviously, the details of the cluster structure or galaxy structure and evolution. So obviously, all of that will influence these rates you predict. But we did, we applied, several limitations to our models. There are, a few caveats, but, when you scale down this, to something reasonable in terms of initial conditions and occupation fraction of intermediate mass black holes, it seems that, we are roughly consistent with observation. So at that point in time was like good enough for us, looking at this paper. But
yeah, great.
Definitely, there is a lot to improve upon this.
Thanks, I'll read more.
Thank you for your question.
Yeah, I have a question for you. And, talking about intermediate mass black holes, they're very hot for the M sigma relation or whatever relation between the black hole and the host galaxy, right? So we all know that at some point M sigma relations or some relations needs to break down at low masses because the black hole becomes so small that it's just unreasonable that it will have any effect on the galaxy. So where is your idea about where in mass scale these relations should start to break down
So the point is that I think that, once you get, if you look here, once you get to say, here, like, in this regime, I think that, the idea is more to look at, down here, like to look at, not galactic centers, but more to globular clusters, where your velocity dispersion is, a few tens kilometers per second, and an MBH of hundreds or thousands solar masses might have, a nice effect. So I do not know, so there are indications, that this might be the case, so if, for example, you look at some of these scenarios, like this or this, you might form something that might agree with like the M sigma relation, but I do not know. I mean, I think it's it's already unclear exactly, like in terms of very massive black holes, exactly how you can model and connect this M sigma relation. So, like for this mass range, it's maybe even more difficult. But let me say that like there are some candidates or evidences for some of these intermediate massive black holes that they might lie on this one. Okay, for example, if you look at this candidate,
Baldassare one, yes.
yeah, so it seems that roughly it gets it lies on this line. So it might be so it might be, but still the error bars are quite large.
Thank you. So is there any more question for Giacomo? All right, so I think we're done. And let's thank our speaker once again for a wonderful talk. And yeah, we will see you for the new season, a brand new season of the BHI Colloquium in September, I guess. And all stay safe. Thank you.
Thank you. Bye.